First of all, I want to thank the organizers. This just seems like it's going to be a really, really fun meeting. And what I chose to do for my talk is basically choose some topics. So I'm really interested in this collection of people and the kinds of shared topics we will be able to discuss. And so I just selected things I wanted to get out on the table to engage in some fun discussions in the course of the week. So that's what I'm going to do. And I really want, as some of you know, my favorite way to give a talk is when there's constant interruptions from the audience. I feel like I'm actually connecting with you that way. So do it, and I'm very experienced in somehow resolving, in the allotted time, bringing it to an end. I don't fret too much if I don't get to say every single thing. I'd much rather engage. So please interrupt as you see fit. So the first thing I want to talk about is, so part A of my presentation is cosmology. And I want to talk about entropy. And part 1 is entropy. And let's talk, so in cosmology we have the standard Big Bang theory that works very well and accounts for just about everything we see. And then we have an extra piece that we tend to add these days, which is cosmic inflation. And I want to first tell you something about just the standard Big Bang theory. And I want to plot entropy on a log-log plot as a function of something that's really the scale factor that we can call time. And in the standard Big Bang, it looks something like this, where we're here today. And in the very early universe, so I'm talking about the entropy in the region of the universe we observe, and we just follow it back in time. And at early times, the universe is evolving adiabatically.
So is this the von Neumann entropy of the quantum field?
Yeah, it's a bunch of stuff. So I'm going to tell. Yeah, so here, and it's a bit patched together, but here I'm just talking about. So here we describe the universe as a very homogeneous state of particles in thermal equilibrium. And those particles easily, you can calculate the entropy, they're in equilibrium. And taking the co-moving region that becomes our observable universe and the fact that it's evolving adiabatically, you see constant entropy on this plot. Then, as you enter another phase of the universe, what's happening most here is, so this is particle equilibrium. And then here we have structure formation. And quickly, the dominant contribution to this entropy that's growing is actually the entropy of black holes. So the entropy of especially black holes at the center of galaxies. But generally, what's going on here that's special and that leads to black holes is the structure formation, gravitational collapse in the universe. And this is what leads to this region. And then here, this is dominated by the horizon entropy of the cosmological constant, which is sort of the ultimate endpoint of this entropy value. And now,
we're not quite there yet. It looks like today is really.
Yeah. We are dominated by the cosmological constant, but we're not quite there. So now I want to look at this plot, and I can take questions. I know this is not everyone knows much about cosmology, and I've not said very much, so there could well be lots of questions. But the point I want to make is that there's a thread of discussion in cosmology, and we've already heard this from Charlie, that we want to explain how the universe is typical. That we're driven to understand that we live in a typical universe. But what does typical mean? Well, we know what low entropy means. It means located in a small part of phase space. And surely that's what we mean by atypical. So when you live in a universe like this, you're drawn to the thought that the starting point was atypical. And this gap between where you start and where you end up or might end up is tempting to call tuning. And it is. So there's the classic tuning problems of cosmology, and in that, one way of presenting those tuning problems is just to say the entropy is low at the start, at the beginning of the cosmos, and that's, well, we do have an arrow of time, and we do have, we expect an arrow of time, and our understanding of the universe is consistent with that, and an arrow of time means, the thermodynamic arrow of time means a low entropy starting point. So this all makes a lot of sense from that point of view, but then you go into the cosmology group in your department, and you find people wringing their hands about this and saying, oh, the beginning of the universe is finely tuned. What can we do about it? Question?
Why would you call tuning the difference between what we have now and what the beginning of the universe was? You would sort of think from what you've drawn so far that, well, okay, maybe the beginning of the universe was special, but sort of all of them will evolve to having this much entropy. So the difference in entropies doesn't seem like that.
Well,
I would call tuning.
well,
Call tuning. How did we get the particular starting condition we have?
yeah, that's what I mean. So I'm comparing it with sort of the maximum. So this is kind of a maximum it could be. So if it were at the maximum to begin with, then I would say there's no tuning, but also no arrow of time. So we're sort of operating in this funny way. I thought I saw another question coming. Yeah.
Yeah, this may not be that germane, but I've never understood this. What do you mean by the cosmological constant dominates the entropy?
So we assign entropy to the horizon of the cosmos. So it's horizon entropy, the Gibbons-Hawking entropy of the Sitter space we approach.
For people who don't have that, then is there a good intuitive way of sort of relating that to other ways of thinking about entropy?
I don't think I have a great one. Does anyone else think they have a great? I mean, I was hoping Adam would try it. Yes.
So the cosmological constant means the universe is doubling in size every 15 billion years, which means there's a cosmic horizon. Because if something's far enough away, the expansion of space-time means you'll never see it. So Bekenstein and Hawking told us that black hole horizons have an entropy given by their area divided by 40 h bar. And so you can also say the same thing about the cosmic horizon, except the cosmic horizon is ginormously larger than the black hole horizon. It's 15 billion light years across rather than much smaller than that. So it's just, that's what it is. In terms of some microscopic counting that explains that, we have some idea how to do that for black holes and no idea how to do that.
That's the missing link. So black holes, you can throw stuff in and count up the degrees of freedom, but yeah, so it's a more speculative thing than.
Is there any reason we think about those two horizons? I mean, it seems like in a general universe we have all sorts of horizons.
Well, these are event horizons, and they.
So yeah, I mean, I get how there's some sort of definition there in terms of whether you can escape out to infinity or at least in the case of a black hole. Is it obvious why these are the only two sorts of horizons we care about when I start adding up the entropy of the universe?
Well, they're horizons that have been treated. I mean, they have a second law associated with them when you combine. Well, with black holes, you combine black holes. The horizon entropy is at best constant or increasing, and they have that form, and you sort of can do that kind of bookkeeping. I've not seen that tried with other horizons.
Right. Yeah, it's really the black hole one I can sort of buy. It's the connection to the cosmological one.
Well, I encourage you to be a little skeptical about that. I think that's the sense I have. Yeah. Charlie.
Well, is there a good reason for believing that the entropy isn't zero? let's say if the universe starts in some definite state and runs unitarily, maybe this entropy is all just entanglement with the part of it that's on the other side of the horizon. So I guess there's another
Sure. I would be, you know, like many physicists, I find that a attractive thought, but it still doesn't stop this analysis from going forward and from the question of tuning coming up. So this is called the tuning problem, and there's also a very famous response to the tuning problem, which is cosmic inflation. And what cosmic inflation does on this plot is it introduces something different here, which looks like this. And you can look at what I just did and wonder, well, if I said this having this gap was tuning, and now I've extended it like that, why is that a solution to the tuning problem? And that's a good question. So this is when I said a moment ago that I find inflation confusing. This is the part I find confusing, although not. I'm going to say some more about it. It's not quite as confusing as it looks on this plot. But let me. Right. So one of the things you then. So this is sort of one set of comments, which is entropy in the cosmos. Now I want to make an added comment. Is to really go further than just waving your hands at a plot like that, is you need some kind of meta picture. So what you really want to know is, well, how would this state come about physically? How would this state come about? How would a standard Big Bang come about? To have inflation somehow deepen your understanding of the universe, you'd want to know that somehow inflation came about more easily than a standard Big Bang or something. So you want this meta picture, and I'll just sort of do a cartoon of what meta picture. So there's some grand thing beyond some super universe here, and maybe we can have a standard Big Bang appear in it, and maybe inflation could appear in it, and maybe it's even in equilibrium. And if it is, so it's sitting at some maximum entropy, and then maybe there's fluctuations, and maybe inflation happens is more likely fluctuation than the standard Big Bang, and you can sort of play these games. But what I would say is that every attempt to make such a meta picture, including my own, are somewhere on the spectrum from ridiculous at one end to hokey at the other. So we don't really get this. This is not a well understood topic. This would be a foundation of cosmology, and we just don't have it. And so really the questions we have about, why is this tuning, what could you do to solve it, end up tracing back to this kind of, what are you thinking is underlying this picture of cosmology? What got this part of cosmology started? Is it part of something bigger? If so, what is it? What kind of evolution gets you into this? And we just don't have a great theory for that, although we're trying. Yeah.
I'm not sure what the definition of entropy really would say more about that as well, but is there any, is this picture that you're drawing, and how far is this backed up by data? Because we changed the picture, that's on the fly. So what do we know?
Good. So I'll jump to a point I was going to make later, because it's the perfect response to your question. So you can ask, I'm going to step back and just say, what are we trying to accomplish? So if you walk the halls of a physics building and ask what people do with their theories and what people do with their initial conditions, normally people are really happy if they have equations for the physics that work, and they just grab whatever initial conditions they need for the equations to suit their experiment, to describe their sample in the laser or their particle collider or whatever. And so initial conditions usually don't matter much to physicists. It's the equations. You have equations that describe the physics. And here we're obsessing about initial conditions in cosmology. And it's partly, I mean, it's a reasonable thing to do because so much depends on them. It sort of defines the whole universe. But if we just sort of started here and said, do we understand the universe? Well, we do in the sense that we have very good equations that describe this evolution, and we know just what initial conditions we need to give them, whether it's here in the Big Bang or at the end of inflation. And the thing is, inflation gives us a nice narrative for how we get to those initial conditions.